So just to say that although things look so severe this year, this is more or less in line with the warming we're expecting. It's just that with such great year-to-year variability in climate, there are going to be years that seem even more extreme than anybody had predicted. And I also want to point out that there has been some progress in reducing emissions. It can seem from the news like everything should be doom and gloom about climate change. And so I'm presenting to you this graph. This is from the global stock, the technical analysis for the global stock take. So this is the technical work being done to feed into a process going on at COP28 starting tomorrow. And it's showing what trajectory we need to be on to avoid 1.5 or 2 degrees of warming, at least a good chance at that. And then where the policies that have been promised under the Paris Agreement put the world. And that's the red area is the NDCs. And so that is where we would be if countries fulfill the promises they've had towards 2030. This doesn't look good, right? This is like way above the 1.5 or 2 degree threshold. But had it not been for the Paris Agreement and those NDCs, that black line of historical emissions would have continued to increase. And so right now, if countries do go ahead and if they do go ahead and implement the policies that have been promised, we're looking at somewhere around a little less than 3 degrees of warming. And there's a big if. Countries have to actually implement all the things that have been promised. But just to keep in mind, if I showed you the same analysis 10 years ago, it would have said we were on pace for 4 degrees of warming. And so there is a lot of bad news about climate change, but there also has been progress. And I think the existence of that progress gets overwhelmed when we see just sort of the daily news of extreme events, that there are some things being done. It's just not nearly enough. And the reason I point this out is because we hear so much about these temperature thresholds. And the important thing to know about the temperature thresholds is they are valuable markers for what the world should try to avoid based on how much warming that governments have agreed would probably be dangerous. But to be clear, they're not purely scientific findings. If they were scientific findings, they would look like pi. There would be many digits involved. They're round numbers, which is what tells you that they don't come purely from science. More than anything, they come from geopolitics. 2 degrees was a number suggested by the European governments for many years. 1.5 degrees arose because small island developing states and other developing countries that have been colonized by Europe were upset that Europeans were getting to choose the number. And so there's a good argument that those countries are much more vulnerable to climate change, but it's important to remember that the lesson of the science isn't so much that we worry about the thresholds, it's that every bit matters, every year matters, every choice matters. And this is straight out of the IPCC, the lesson being that yes, we want to avoid these levels of warming, but 1.6 degrees is still better than 1.7 degrees, which is better than 1.8 degrees. And so the more we reduce warming, the less the impacts are going to be, and less the environment and people will suffer. And so from that, I want to sort of bring this back to the sort of things that you're all dealing with in your organizations and your communities. This is a picture is from Lytton, British Columbia, after the fires 2 years ago that effectively wiped out the town. There's a lot of questions these days about what do we do and how do we think about extreme events like this. There's a couple basic ways scientists do it. One is to look at the physical principles and to say, well, as the planet's warming, we expect a shift in the distribution of the weather. You should see more extreme events. And then we can also look at the physics, the physical dynamics, and saying, well, also, we would expect the jet stream to get a little bit more sluggish and weather systems to stay in place for longer. And there's a lot of science behind that, why that would be the case. So that could explain something like the heat dome and the fires that were experienced out here in British Columbia a couple of years ago. The other way we do this is through what's called event attribution research. And this is very similar to what epidemiologists do. It's sort of similar to asking the question, does cigarette smoking cause cancer? I think everyone on this call would agree that it does, but that doesn't mean you could say for sure that a certain person's case of cancer was caused by smoking, right? It's a sort of wrong way to ask the question. And so climate scientists, the reason you hear attribution of extreme events all the time now is climate scientists have learned from epidemiologists to ask the question a different way. So we ask it probabilistically, what are the odds of something happening with and without climate change? And so for that heat dome, for example, the evidence showed that it was like 99% attributable to climate change, and that this level of this type of event would be 100 to 200 times more likely if we get to 2 degrees of warming. So it was a really extraordinary event. Because it was so extraordinary, we can say that there's like a greater than 99% chance it couldn't have happened without climate change. It doesn't mean heat waves couldn't have happened in the past, but maybe this particular one couldn't. But there's a detail in here that I think is really important for all of your work. This is just some records that were set during that heat wave. The analysis about it showed that one of the challenges is we don't have a perfect record of what was possible in the past given climate. So if you think of climate as a sort of range of conditions that are possible, in the real world, we're only running the experiment once. So we only get to experience one time what range of conditions could occur in a given climate. And so when they went to do the analysis for the heat dome, it was so far outside the realm of past experiences that just doing the extreme value statistics was difficult. I can sort of show you the graph they used for the analysis. All of those little check marks, those plus signs, are all previous heat records for the region. And then the purple line at the very top was what was experienced that year, averaged over the region. And basically, to try to assign some statistics to this was almost impossible because what we experienced was such an outlier. And that's a really important thing to keep into mind when we're thinking about planning for the future. And I'll come to that again in a second. When we're thinking about the biophysical impacts across Canada that are relevant to biodiversity, it includes heat waves, right? Warming, which is happening faster in winter and in the north. It includes the impacts of that warming, like more frequent fire weather, not necessarily forest fires, but the weather that can cause them being more frequent and more severe, and then associated smoke events that can come with it, like we all experienced last summer. And then all the other things that come with extreme heat, drought and water stress on plants, obviously very important for biodiversity. And if we think about the water side of this, warming also means more rain falling rather than snow, which is particularly an issue in the mountainous parts of the country, like out here in British Columbia. It means the timing of stream flow will be different when the peak happens in the spring, which has all sorts of implications on biodiversity. We also expect to see more extreme rainfall in a warmer climate. There's already data on this, and there can be flooding impacts, but whether rainfall turns into flooding, it's really about land use as much as it is about the rainfall. And then if you're on the coast, those of you, I think a couple folks here from out east, folks that are here out west, there's obviously concerns out east about growing increases in hurricane intensity and the related impacts. And on every coastline of Canada, risks of sea level rise. This is a photo taken during a very high tide here in Vancouver a couple winters ago. And so when we try to look into the future to say, what is this going to mean and how we plan for biodiversity, there's a variety of different tools you can use. And then the question really comes down to what scenario do you want to plan for? So this is from a website called climateatlas.ca, which is a really helpful tool. I recommend folks take a look at it if you've never have, where you can go municipality or region by region. It breaks Canada up into a grid, and it has downscaled data from global climate models that give you a range of predictions for different future scenarios, right? And so this is what I really like about Climate Atlas, and the next slide I'll show you, is it's showing you this not for standard boring climate variables that folks like me look at, but by the sorts of things that people in cities and urban areas and folks who work on biodiversity think about. How frequently is it going to be really hot? And so this is the number of very hot days projection for Toronto. But what I'm showing you is for what we would consider a middle of a road scenario. This is basically the scenario, like about 2.7 to 3 degrees of warming scenario that we're on pace for, given if countries are successful in implementing current policies, right? So that's one example. Here's another example. This is from a different website, uses the same data. It's a different group of folks that did this, called climatedata.ca. This one's more government done. It's the same idea, but here we're saying, how hot are the nights going to be in Vancouver going forward? This is really important for not just for organisms, but obviously for people. It's warm nights that often do the most damage in terms of human health, but also some ecosystem health. And showing you the difference depending on the scenario you choose, right? And so RCP 2.6 is a low warming scenario where we mostly meet the Paris Agreement goals. RCP 4.5 is what we're on pace for. RCP 8.5 is a really extreme scenario that's unlikely to happen. We'd have to burn a lot of fossil fuels to make that happen. But it shows you how much the projections depend on the range. And so one of the challenges when you're thinking about planning with climate change is deciding which future we want to plan for. Is it the high end one? Is it the low end one, et cetera? A lot of people will tell you plan for the one in the middle, because the one in the middle is the most likely future, right? Others would say plan for the most extreme one, because what if we have to, take the precautionary principle? What if that comes to pass, right? But here's where it gets challenging. A lot of the impacts on biodiversity and of climate change are not things that you can do straight from climate data. This is an image of a barge that was tied up in Vancouver. It's a cement barge. It sits in out in the water in the bay in Vancouver most of the year. I pass by it in my kayak all the time. And then during a high tide, it got wedged off it broke off of its mooring. And the water level was so high, with sea level rise contributing, that it got wedged onto the beach in Vancouver, sat there for a long time, and they just had to dismantle it. They couldn't get it off the rocks, right? This is not something people would have predicted, right? Because the climate model is not going to come up with this scenario. And so one of the things to keep in mind when you're thinking about the impacts of climate change and whatever system you're studying is that the extremes, the very hyper-local impacts, and compound events, combinations of heat wave leading to a forest fire, which then leads to the soil being weak and causing a landslide months later, those are the hardest things for scientists to project. And so you kind of need to target your planning and your thinking for these kind of low probability, high impact events to some degree. And this is where that point about how well we know the existing climate comes into play. This is a picture of the flooding outside of Abbotsford that happened in 2021 that cut the city of Vancouver off from by road, train, or anything else from the rest of the province and the rest of the country. We have data limits and trying to figure out what the worst event could be, right? In that we don't have a full representation of what was possible in the past climate. And a lot of our past planning wasn't even good enough for the climate that we had, let alone for the climate that we're going to experience. And so for that reason, the projections sometimes, even if the climate is changing on average, how scientists expect, it doesn't mean that we're going to correctly project the extremes. That is the hardest thing for science to do. And as a result of that, we might want to design our thinking, whether it's planning adaptation for urban areas, whether it's about biodiversity, to plan both for the fact that Canada and the world is hopefully going to be successful in dramatically reducing emissions and getting towards net zero, but also be ready to withstand that high warming scenario. It's not likely to happen, but it might better represent the extremes that we could get even in a moderate warming scenario, right? So we need to sort of think about the long term in that case. Last thing, just to note, COP28 is starting tomorrow. I do a lot of work on climate policy, and I'm happy in the Q&A to also talk about what's happening at COP28 and the major things up for negotiation. So thanks, everybody.
Thank you very much for that presentation. It was perfect. It was exactly what I had in my my head when I was looking at how this could, and I hope everyone on the webinar has found it as informative as I have. I think what I'll do next is I'll have Dr. Kerr present, and then I'll have the Q&A afterwards. So if you could just hold your questions and answers at this point for questions, then the answers will come. And over to you, Doctor.
Thank you very much. And I will be picking up after that superstar presentation from Dr. Donner. That was a wonderful view of climate science and its implications. And now we have to try to understand it. And just before I kick things off, if someone could give me a thumbs up if they can actually see everything that I'm doing. Okay, good. I'm going to talk about some of the ways in which climate change is felt by species that we may have an interest in protecting. Not really going to talk about the same sorts of issues that Dr. Donner talked about in terms of how we know climate change is real and our approach probabilistically to understanding things like extreme events. But one of the things, well, many of the things that he said, but one of the things I'd like to just hold on to from what Dr. Donner said is thinking about how extreme weather is growing in frequency and severity as we see climate change progress. So please hold on to that thought as I go through my presentation today. We all want to conserve biological diversity. There's no ethical dilemma to be understood there. We want to try to protect biodiversity, and there's a million reasons why that's true, and that those million reasons have individually been studied by many researchers over many years. Independently of our specific knowledge regarding land use change and habitat loss and climate change, we know that extinction rates today are perhaps as high as 10,000 times what they would be in the absence of human activity. The actual range there is between 1,000 and perhaps 10,000 times as high as what we would see in the absence of human activity. And you can measure this kind of thing simply by assessing the status of species over time and how those statuses have changed. If you consider those kinds of problems at a global scale, there are now entire books that have been designated or are focused on trying to measure extinction rates today and comparing those extinction rates to what would be going on under natural conditions. And by natural, what I mean is absent the sort of copiously unsustainable things that humans currently do. So take it as given, based on multiple independent lines of evidence, that extinction rates today are between 10 to the third and 10 to the fourth, the rate that they would be in the absence of human-caused environmental changes. But let's turn a little bit toward the challenge of climate change. I think historically speaking, we probably all know that in the past, perhaps up until the 1980s or even the 1990s, the major preoccupation of conservation biologists was trying to understand how patterns of habitat loss, so habitat loss and fragmentation, how those things would affect our prospects for conserving biological diversity. We also focused on things like invasive species and overkill, so overhunting, and things of that nature, but we were not focused particularly on climate change. And up until around the 90s, we didn't have much direct contemporary evidence that climate was beginning to exert strong effects on biological diversity, either within regions or at a global scale. But here are some foundational principles that we know are true, again, from multiple lines of biological evidence. And in a biological sense, we would say these are accepted facts in biology. One of these is that species are limited in what they can tolerate. Now, this is intuitively true because, of course, all species have limits. That's almost a logical requirement. So in some ways, a very uninteresting thing to say. But the reality is that those limits differ among species. And if you exceed them, either because conditions became too hot or too cold, too dry or too wet, those species will be confronted with challenges within particular environments, and they can go extinct. Now, the way that actually happens is not like flicking out a light in a room where you just switch off the light switch, okay, boom, they're extinct, and suddenly no one could have seen it coming. What actually happens is that when conditions become more extreme than a species is able to tolerate over a sustained period of time, their population growth rates go negative and populations begin to shrink. And obviously shrinking populations are problem populations. So if they shrink for a long time, the population will wink out of existence in that area. But the thing is, climate change is a process that is occurring over a very large geographical area. In fact, it's a planet-wide thing, but from the perspective of a species, the only places they can experience climate change are across their geographical range, the places that they are found in the world. So what happens to a species' geographical range when climatic conditions or other conditions change? There are really only two things that can go on. Well, three things if you count that. The first thing that can happen is they endure it. Some species are very good endurance athletes, so they can persist despite almost anything that we can throw at them. Let's take that group of species, which include all kinds of things, some of which are not very exciting for many of us, like dandelions and mosquitoes, and we'll put them in a box and we'll say, these are the things that are not going anywhere bad in the sense of extinction because of climate change. They might be going somewhere we don't want them to go. Mosquitoes can expand their ranges and so on. But the other things that species can do beyond just staying in place and toughing it out when climates get hot is they can expand their range into places that used to be too cold, or they can go extinct from places that have now become too hot. And when you put those extinction processes together with range expansion processes, what you have is a geographical range of a species. We'll do a north-south geographical range. And there is this expectation that those species may expand to the north, if they're in a place like Canada, and contract from the south. So the whole geographic range shifts towards the poles. This is one of those areas where there is an important intersection between climate change and land use change. The capacity for species to colonize new areas is going to be affected by how permeable the landscape is that they must pass through. A habitat that is relatively continuous for that species is one through which movement might be expected to be easier, so maybe they can expand faster or go farther when habitats are continuous. When habitats are fragmented or that consist primarily of intensively used human-dominated areas, many of the species that we are concerned with, that is not the mosquitoes and not the dandelions of the world, may find it very difficult to get through those landscapes. Then we've got a problem. Maybe what happens is that instead of species expanding their range to the north into areas that used to be too cold, they get stuck because they can't move through those landscapes. And then what happens is the places that get too hot still get too hot, and the species range begins to contract from the south without expanding in the north, with the consequence that you get range contraction overall, which increases species level extinction risks. The general impetus from climate change for northern hemisphere species is that species will need to move further north or further up. In other words, they are going to be shifting into places that are perhaps yesterday were too cool for them, but that today have now become warmer and therefore potentially a space they can occupy. So let's consider how we would think about this challenge from the perspective of big picture analyses. So we think climate change poses risks for biological diversity for a few critical reasons. First of all, species have tolerance limits. There are conditions beyond which their survival is unlikely for various direct and indirect reasons that have to do with physiology or the things that they eat, what they interact with in the environment, and so on. The second fact is that climate is changing rapidly. We might parenthetically note that climate is changing rapidly because of human activities. And finally, we'll note that new conditions as a consequence of climate change, but other forms of environmental change too, might now exceed what species can tolerate. So how are we going to understand what's going on with biological diversity, given that we've got perhaps 5 million species in the world, but as many as plausibly 20 or 30 million species in the world, and they're distributed over gigantic areas? The short answer to that question is we have to study species that are very well and intensively collected for any reason. It doesn't matter why people want to study these things and that we have a lot of data for them. It just matters that we have a lot of data. So here's a group of those species. Shown on this map, this is all of the observations for bumblebee species collected between 1901 and 2015 that exist across hundreds of databases globally across Europe and North America. So it's not the entire world. It's relatively well-studied parts of the world for a relatively well-studied group. And the question is, what's happening to this group of species, given the points that I've raised here on the left-hand side of this slide? So species have tolerance limits, climate's changing, and new conditions might arise that species find intolerable. What's happening is that these species are disappearing from the hottest places that they historically occupied. Species are globally, these bumblebee species, when I say globally in this instance, what I really mean is across continents, they are shifting toward cooler areas on average in a very particular way. They're shifting further north in a sense, and they are moving further up in elevation. So they're moving up the sides of hillsides and mountains towards higher elevation areas where temperatures are cooler. But when I say that they're shifting further north in a way, what I really mean is that their average range, the average latitude, for example, of their geographical range is shifting north. But the reason it's shifting north is that their southernmost populations appear to be disappearing particularly frequently. So on average, it looks like their range is rolling up towards their northern margins. On average, bumblebee species have increased their elevations by about 300 meters over the course of the last 35 years or so. Evidence then that population level extinction is currently going on among many bumblebee species. And understand there's about 250 bumblebee species in the world. Our study included around about, well, almost 70 of them. So not all bumblebee species, just the ones we have good data for. If you look at the geographical range of these species, what I want to try to do is summarize a generalized statistical pattern using this figure. If you examine the geographical range of a bumblebee species and look at the nature of this discovery, what you find is bumblebee species are shifting upward to cooler elevations. And if we model in a purely hypothetical sense what that would look like, this is it. So starting with the 1980 or so geographical range of a hypothetical bumblebee species that shows the average response of bumblebee species across Europe and North America, that species is kind of evaporating in terms of its geographical range. So it's present, for example, across much of Saskatchewan, but if it shifts upslope by 300 meters, many of those, well, the majority, vast majority of those populations disappear. This trend is underway. So when we talk about what we think climate change is going to do, these patterns are likely to continue into the foreseeable short-term future. That is, over the course of the coming decades. The things I'm describing here are already things that have happened. So these are what we have observed already to have happened. A much warmer future raises the distinct possibility that some of these bumblebee species we have looked at will experience climate change-driven extinction. Okay. Something that's really important for us to consider in understanding how climate change affects biological diversity is that when we talk about climate change, and Dr. Donner's expertise here, I'm sure this will feel like a very familiar thing to say here, climate is the long-term average of weather. This is really important from the perspective of biological diversity because most species never experience climate. They only experience the weather. The majority of species don't live longer than a single year. That's virtually all species that are out there. They live 1 year or less. They don't experience long-term averages of anything. They live maybe 1 spring, 1 summer, 1 fall, and 1 winter, but that's it. And then it's lights out and the next generation takes over. The consequence is that if we want to understand something about how climate change is going to affect species, the only way we can really get close to real mechanisms for how it happens is to evaluate what happens with the weather. And this is where we start building this link with the severity and frequency of extreme weather events. Understanding and measuring how extreme weather is going to affect species on an individual basis requires that we know something about the limits of their tolerance. But the limits of their tolerances differ enormously from one part of the year to another. So if we consider that their tolerances show annual variation, then what we can do is start comparing what monthly, weekly, daily, even hourly temperatures look like over the course of an observation period and say, historically speaking, the conditions we observe in January or the conditions we observe in July are perhaps exceeding what was normally experienced in a climatic sense by these species anywhere in their geographical range. And if we take a very conservative assumption that if a species is experiencing weather that is warmer than any climatic condition that they have over the last 100 years ever experienced in a measured way, that we have ever measured that they have experienced, then we can say they are accumulating interaction with extreme conditions. Now, the extreme weather here is a species-specific measurement of extreme weather. And that's important. This is what we are going to call a thermal position index. But that's a thing that we have created as a metric for this, and it's not important to remember terminology like that. But what actually happens if you measure something like the changing frequency of extreme weather relative to what a species has historically experienced, that is, any time over the last 100 years of direct, continuous weather observation in well-studied places like North America and Europe? And what you find is that populations of, and this is with bumblebees again, have started to show patterns of change that relate to the frequency and intensity of those extreme weather events. Differences in extinction colonization dynamics is biologically what we're really getting at here. But if you examine it you can use different kinds of terminology. And basically what happens is if the heat waves in the summer get really, really bad, these populations show an increased frequency of disappearing. And that is a quantifiable link. This is what happens with bumblebee species. This was recently supported in a new analysis that was published in Nature about a month ago now, maybe 6 weeks ago. So these findings for bumblebee species are very robust. And in fact, we can recreate these findings within individual bumblebee communities. And what you find is that the frequency of extreme weather actually predicts community level dynamics in bumblebee species, but that's a paper that has not yet come out. Okay, but if we were just talking about this is the change in exposure to extreme conditions. And this map actually illustrates differences in the likelihood of species being present from one place to another across areas in Europe and across areas in North America. So it just illustrates the logic and empirically evidence-based finding that I just described. And this is the spatially explicit measurement, essentially, of species either persisting, colonizing new areas, or going extinct relative to changes in extreme weather, as well as differences in land use. Put those two things together to understand what's going on with the trajectory of these species. If we were just looking at bumblebees, and that was the only group for which these observations successfully predicted dynamics, then we would have pretty limited evidence that this kind of thinking for climate change was consequential for biodiversity. The reality is that exactly the opposite thing is true. The results that we have generated and that others have now generated as well regarding the frequency and severity of extreme weather has been tied to geographical range losses among vertebrate populations globally, as well as insect populations globally, and certain plant groups as well that we have data for. So these results appear to be true for virtually every taxonomic group that we currently have any way to measure. And we know that these ideas also work for groups like birds if we think about their populations as well. Extreme weather is very consequential for especially juvenile bird mortality rates. In other words, the findings that I'm describing are significant not just for bumblebees, but for life on Earth. And that should worry us. So one of the things that I wanted to say here, so where are we so far? Extreme weather can affect species across spatial scales, whether it's those individual quadrats that I showed you in areas like Europe and North America, or it can do so measured across entire continents. The thing is, we also know that there is an extremely strong interaction between habitat structure and the extent to which a species is exposed to the growing frequency and extremity of these weather events. This is one of the ways in which I think our understanding of habitat management can offer us hope for conserving biological diversity in an era of unprecedented anthropogenic climate change. In other words, habitat loss and climate change interact. To understand that interaction better, we've got to consider what goes on at the level of individual habitats. And without getting into this kind of thing in extreme detail, I will just say that we have recently extended the models of what we have constructed across continents to be able to improve predictions of dynamics of individual butterfly species within habitats, and doing this with centimeter scale resolution microhabitat or microclimate measurements using thermal infrared airborne photography on a drone, so an unmanned aerial vehicle or UAV. Take these super high resolution photos, convert those photos into species-specific tolerances that assess how the conditions locally may exceed a species tolerance or not, and then predict how abundant those species are. And it turns out that that thermal information is really important. But one of the biggest things that alters the thermal characteristics of these habitats is whether or not the habitat structure is complex. If we conserve habitats, don't clear them out and turn them into cornfields, what you have is a habitat with a great deal of microclimatic diversity. And this provides ways in which species are able to essentially hunker down during the most challenging parts of their life cycle and avoid or reduce the effects of extreme weather. And these results, it turns out, are very robust also when we consider bumblebee species. So we're starting to collect multiple lines of evidence that these models work within habitats as well as across continents. So just quickly to summarize, the growing frequency and severity of climate change related extreme weather has already begun to alter the distributions and abundances of species, measurable at continental scales, but also within individual habitats. That discovery is now validated for many species groups in virtually every part of the world. But the take-home message here, from my point of view, is simply that managing habitats for microclimates can mitigate in the short term the most concerning effects that climate change can impose on biological diversity. And it gives us one of those bridges to the future that buys us time to begin to get emissions much, much more under control from a conservation point of view. And with that, I will conclude. And perhaps like Simon, I'd be very happy to take questions.
Thank you very, very much, both of you. It was so informative. And this morning we had Dr. Bill Reese present to the full staff meeting. And there's so much of this information is, you want to have hope. And like we said, we're not going to leave you depressed. But I know a saying that from Edward Abbey, when I was a teenager, it was like, sentiment without action is the ruin of the soul. And so, the part of this whole webinar series is, with this amazing information that you're sharing with us, we want to continue that along, and that will be part of the series. But enough of my plug. Let's go to Q&A. So the first one is for Simon, and it's from Thorsten Arnold, unless it's the opposite way. The scientific consensus is relatively quiet about the differential warming of oceans, no land use change, and a much stronger warming signal on land, combining GHG warming and direct biophysical changes, including the small water cycle. Are climate scientists appropriating the heating of the land that is also human land use change in order to popularize all observed weather extremes? That I can throw that in the chat. Anyway, I think you might be on mute, or did I have you?
No, I'm happy to. Thanks, Sarson, for the question. So you're speaking to a true result of data. The ocean surface in the deep ocean is not warming as quickly as the land, if you look at the data, and the main driver of that is just physics. It's just that ocean has a higher heat capacity. Water has a higher heat capacity than air, so it just is not. It takes more energy to warm water than it does to warm air. So as more energy is being trapped in the climate system by addition of greenhouse gases, you're getting to the air should be warming faster than the ocean. So it makes sense. Now, in terms of the contribution of other things other than greenhouse gases to warming on land, there's two considerations here, I guess. One would be, as cities expand and urbanize, the urban heat island effect grows. The fact that the downtown of a major city tends to be warmer than the countrysides, particularly at night. It doesn't cool off as much at night. And so that is the main reason that climate scientists, when they analyze large-scale patterns in temperature, do not use weather stations that are in the middle of cities, because those cities may have grown over time. So the change in the temperature at that weather station might be influenced by the local land use change. And so there's been tons of research on this. And so all these estimates of global average temperature that you see are based on stations where there has been minimal change in the surrounding land around the station over time. And that's sort of where the robustness of the temperature results come from. So this is something that's pretty well studied. The other way that land use change, of course, could affect temperature is by changing the land surface to, if you go from a forest with really dark green leaves to a cropland or something else, or shrubland that has brighter leaves, you will reflect more incoming radiation. And so that's sort of a change in the reflectivity that could affect temperature as well. But all the analysis shows that on net over the planet, that's not really contributing very much to warming at all. And so really there isn't the difference between the land and ocean is just goes down to the physics of how the planet is warming due to the enhancement of greenhouse gases. There isn't really another major driver. So cities definitely, city of Vancouver, city of Toronto, et cetera, have probably gotten warmer over time, not just because of greenhouse gases, but also because of the urban heat island effect. But that's not factored in to the global, that's purposely, when the global analysis is done, we purposely leave those examples out to make sure we're getting a representative global number, not something biased by a few weather stations that are in cities.
Thank you very much. There's another question here. Sorry, I know Thurston, you had another question for Dr. Kerr, but we're at time, so I guess I'll just run these next two, and if you two have to leave, and I'd also, if you wouldn't mind, you have all their contact information, so if you have any real critical questions, I imagine they wouldn't mind answering them. Sorry for. So this is questions for the both doctors. What are some of the things that people who are on low income can do to help make a positive impact in climate change and biodiversity? You'll start, Dr. Kerr, and then just flip it.
That's not a hard question. This is I don't have anything innovative to say in response to this question, but I think the question is really important because there's a really, really critical equity component to climate change solutions as well as to climate change impacts. The worst impacts are felt by the poorest people at a global scale, and the least able to absorb those impacts and adapt to them. But in terms of the answer to this particular question, I don't have anything innovative to say. I think that the conventional thinking around trying to eat lower down in the food chain, reducing things like meat intake, these things apply virtually to everybody. But I would say that it is, the burden of CO2 emissions or carbon emissions should not fall primarily on the backs of the least economically empowered, because the emissions from the least economically empowered people are not especially flexible, but include very, very few true luxury emissions, if you think about what that might mean. And that can be conspicuous consumption, for example. So I think opportunities for efficiency in terms of greenhouse gas releases are much more obvious, not among those members of the population that are in the poorest parts, but among the wealthiest parts. So I think there are things that everybody can do, and they're very obvious. Take the bus, ride your bike, eat more vegetables, eat less meat. But that's not where the deepest cuts are going to come. That's my highly simple answer, because I think that the burden is actually needs to be carried elsewhere in the population.
Dr. Donner, do you want to add anything?
The first thing I'll just say to this is I really appreciate Dr. Kerr's answer. This is like, listen, we won't claim to be the experts on this, but what I can say is that, most of the research shows that while there are all sorts of things that individuals can do to reduce greenhouse gas emissions, reduce their impact, their carbon footprint, or just reduce their impact on the planet overall, most of what we need is collective action, right? That one individual person can only do so much regardless of income. I mean, obviously income makes a difference, but and so for that, I think the most important stuff are the political actions, right? Which is voting, writing letters to your representatives. We actually did a study a few years ago that kind of showed that actually writing a physical letter is quite effective relative to all sorts of other things. And so I would just say there's a lot you can do, and maybe you don't have to think so much about the physical actions you take in the world, but more the political ones.
Which is a nice tie-in from Ron Prickett. What role should scientists do to combat the rejection by political leaders such as Smith and Ford to our need for carbon dioxide reduction and importance of biodiversity of ecosystems? How can we move from a more populist argument that the environmental considerations means a loss of prosperity? And I know I think this may have to be the last question just because we're at 2:04. I don't want to keep people too long here, but or like I saw you actually, Dr. Donner, you were responding to one by typing, but anyway. You want
me to start, or Simon, do you want to start with this one? You know, like Dr. Donner, I spend a lot of time in the policy world, you know, and mostly at the political level. I guess historically, though these days I'm also doing a lot of science advice at the sort of agency level. And so if you kind of dig into this, you know, the traditional way that groups that engage with government really hard look at this problem is that there are people who are unreachable, and you're wasting your time by talking to them. I don't know if Smith and Ford are on that list, but it is possible that one or both of them are on that list, and that you just basically are wasting your life by having the conversation. Having said that, now that is a possibility, but I don't think that that's the way to go, because, you know, my experience in dealing with challenges that arise because of political populism is that there's sometimes the front door is locked, barred, and secured with a portcullis, but what you can do is you can go in the side door, and, you know, find ways to talk about problems that are not specifically climate change, but that are appealing for ideological reasons to people who are not inclined to believe the evidence on the face of it. So, you know, if you can have a conversation, for example, about the potential for economic opportunity by embracing emerging energy technologies, that's an example of a vehicle that lets you have a sensible conversation with people whose only focus is prosperity, and you can do things that are helpful in that direction for climate change. But if you start by saying carbon dioxide emissions are rising really fast, and it's principally because of fossil fuel burning, and you do that in Alberta, you've probably limited your potential to have a conversation extending past a single sentence. So I think there's ways that you can make progress with this, but you have to, you know, there's a lot of listening that needs to take place. And the key is to change your approach so that the audience you're speaking to finds common ground with what you're attempting to get done. And that may mean that you don't really say climate change at all, which is, I agree, not a very satisfying outcome. But these kinds of challenges are, in my experience, you know, ways in with thorny political problems, not reliable ways in, just prospective ones.
Great answer.
No, that was a terrific answer. I'll just add to that. You know, you just with anybody, whether it's a politician or a family member or a friend, I mean, you connect over values. Who people trust depends, you know, what information people trust depends on whether they trust the source, right? And so sometimes people, you know, will say to myself, I'm sure it happens to Dr. Kerr as well, why aren't you yelling at whoever? Why aren't you talking to this person? I'm like, I'm not the one they're going to listen to, but I have to partner with people they might listen to, right? And so that's one of the tricks. And the other thing is to say that you can also, they might not be the ones that are going to listen, but I think with people who will, provide evidence for the counter argument that climate change, you know, and my, like the TED talk I gave is effectively about this, is that, you know, the evidence is pretty clear that a world in which we've dramatically reduced emissions is one in which people are healthier, the air is cleaner, you know, less air pollution, and things tend to be cheaper according to most of the models, right? Because over time, operating an electric vehicle, using a renewable electricity grid, heating your home with electricity is actually cheaper. The challenge right now is that we need upfront investments. And so it's cheaper on average in the long run, but you still have to purchase an electric vehicle, right, upfront, or purchase a heat pump. And so what governments need to be doing now is need to be convinced that the upfront spending is worth it, right? And so for folks, I won't speak specifically to Daniel Smith or Doug Ford, but that's some of the thing. They're like, this isn't worth the energy going into the transition. We don't think it's, and they're betting effectively against it happening, particularly in the case of Daniel Smith.
Great answers. I wish we had more time, but I could see people dropping off now. So, well, actually, that's quite a few still stayed. So that's great. And like I say, all the contact information is there in the invite if you do want to continue this conversation. And again, I hope you continue on this as part of our webinar series as we go on this journey of bringing in solutions and the things that so many of the groups that are on this webinar are already doing. And it's celebrating their successes and because it really is, like I say, sentiment without action is the ruin of the soul. So there's just so many amazing groups doing so many amazing things already. And we just need to amplify that, of course. But anyway, I will stop it there. But I can't thank both you, Dr. Donner and Dr. Kerr, for your time today and your years of knowledge and wisdom and passing this on to us. And yeah, very grateful. And thanks to all the participants as well for attending. And yeah, sorry, I wish I had more time for questions. I think that was my screw up at the beginning. But anyway, I'm going to be following up. I'll be sending a follow-up email as well with the recording and the next steps. So again, thank you very much. Greatly appreciate everyone who's on this call today. Have a great day.
To be able to join you today. Thanks for the opportunity.
Thanks, everyone. Thanks so much.
Thank you. Bye for now.